All right, welcome to the second lecture. The good news is these lectures only last about 10 minutes a pop, so hopefully it's in digestible bite-sized amounts. The last lecture, we introduced some basic definitions about ordinary differential equations and showed how to get the solution for the complementary solution for a first-order differential equation. If you have higher orders, that just the solution gets a little more involved. But here's what we found. The complementary solution, which will be used to get the initial condition response, is y equals the initial condition, or just some constant, e. This is the root of the differential equation, or the eigenvalue, or the pole, t minus t0. T0 is simply where you start. So you've seen this before. So as we go forward, we're going to be developing analytical tools. So we can introduce our first couple of tools. And by the time we can solve all the differential equations, we'll actually have pretty well brought them all to bear. So here's the first one. It's called the time constant. All right. Now that's 1 over the absolute value of the real part of the root, or eigenvalue, or what have you. Okay. It's generally written down as tau. We have that here. And so that's where we take the real part and take the absolute value. So if the real part is negative, we get a positive number. So let's just take a look at that. So let's say you take a look at the characteristic equation. You say, oh, lambda equals minus 10. No problem. Then the time constant is 1 over the 10, take away the minus sign. So it's 1/10 of a second. All right. And then suppose we had a complex root. So the root's minus 10 plus 30i. Well, we completely ignore the I part. And why is that? It's the real part that covers how the thing attenuates to zero, comes to steady state. This part just represents, frankly, oscillation. We'll see more of that. So we ignore that. So we then have 1 over 10 seconds again. The negative part, we just ignore it. Then flip this thing, and here's what we have. Now, suppose the root was plus 6. All right? Well, then the time constant is not defined, because when we just did our last problem, if we popped out a plus 6 for that root, it would say, here's our solution. Y equals y0, e to the 6t. This is a solution for the complementary solution, but nobody cares. In the world of systems and controls, if it blows up, we're done. Knowing it blows up is a sufficient answer for us. It tells us if we have to work with such a system, we need to add a controller to stabilize that. We got to make that into a negative number. Once you know this, don't need to analyze it any further. It's blowing up, and knowing that is useful enough. Okay, so there's our first tool, understanding time constants. This takes us to our second tool, which is built on top of tool 1. All right, so for roots with a negative real part, meaning they're stable, they attenuate, they reach steady state, they're not going to blow up. If it's a positive real part, you're blowing up, so we're kind of done there. So if you have a negative real part, we can define what's called the 2% settling time. Now, to be perfectly blunt, most of the time people just say settling time and they drop the 2%, but I'll show you why that's relevant. And that is defined as to be equal to 4 time constants. Why do we do this? Well, let's just start playing with this a little bit. So let's say we had a system with the complex root. All right. So we ignore the complex part. We'll note, first of all, it's negative, so it's stable. It's not going to blow up. Now I ignore this. Okay, so then given this part, the time constant would be, ignore the minus sign, 1 over 10, and then multiply by 4 time constants. So it's 0.4 seconds. Okay, and here's what happens. So if here's my complementary solution, what it looks like. So some initial condition, don't care about that, e to the minus 10t. And I'll notice I can rewrite this as e to the minus t over tau, okay, because the time constant is 1 over this real part, okay. And where the time constant, let me just fix that here. That should be, make it look a little more like a time constant. There we go. So picture that. So we had, I want to see what the response now is at the time of 4 time constants. Okay, so if I stick 4 tau into here, I'd get e to the minus 4 tau divided by tau. So I can just divide the taus out. Okay, so when you're at 4 time constants in terms of time, this piece here will be e to the minus 4, always. Okay, so y0, don't care about that, e to the minus 4. Well, that's 0.02, whatever the initial condition is. So 98% of the initial condition has been wiped out. It's gone. Goodbye. Sayonara. Okay? So it's 98% attenuated. Hence, we call this the 2% settling time. There's only 2% of the way to go. And you might go, well, hey, there's still longer to go. Why do you do that? Well, here's the reality. With a lot of machines, as they're responding, okay, they're going to look something, if let's say it's first order-ish, it's going to look something like this, okay, in time. Well, that's fine. As you're getting within 2% of this final value, the slope of the line, think about that, the slope of the line is the velocity. It's almost flat. And so the velocity is really slow. And what will often tend to happen is you have nonlinear effects, and friction, when you get within 2%, might stop it right there. So when you're within 2% of the final value, you're really close to the end. And you may have already passed it. The friction, it may have stopped it a little ahead of that. So the standard accepted level for what is the settling time? We go with 4 time constants, at which point 98% of the initial condition has been wiped out. And that's usually pretty close to where this thing is done. So, pages stick together. I'm doing this, by the way, in July, and it's hot and humid. All right. So here's what I want to take note of, is that if you know the initial condition and you know lambda, we can plot the initial condition response, IC, for every unforced first order ODE. We don't have to think about it. Okay? We have whatever the initial condition is. Here's the time constant. Okay? 4 time constants go out. And basically, you're going to start at y0 and either die out here. This is assuming it's stable. You have the pole is negative, the root. If it's positive, it's going to blow up, and boom, there's the solution. So just knowing the initial condition and the time constant, we can simply draw what that's going to look like. We don't have to solve the differential equation anymore. We're going to be moving to more complex stuff, and the story is going to be exactly the same. All right, so we're going to end right here, and we're going to start taking a look at forced responses and how we handle them next. Talk to you soon. Bye.